In 1965, Vice President Hubert Humphrey visited the NASA Flight Research Center hangar where the three X-15 aircraft were located, and the youngest X-15 pilot, Captain Joe Engel, greeted him at the aircraft. The VP asked Joe, when would we be getting a squadron of X-15s? A challenge for Joe to respond without addressing the VP's unawareness of the flight research mission of the X-15 program. Across the hangar, I was standing by the roped-off LLRV on display, and the VP stepped over the ropes and shook my hand as I explained what the LLRV mission was about.
You can see frost on the belly of the airplane there, where it froze due to the cryogenics in the tanks. And we also jettisoned some propellants prior to launch to cool down the fuel lines and prevent vapor lock. When you launched, it felt like you were fired off the shackles. You actually fell away at zero gravity, but it felt like you were fired off. But once you got the engine lit, you got the lift back on the airplane and left the launch scene fairly quickly. It's a photograph from the B-52. Now we're looking down the left side of the fuselage of the X-15. That's the left-hand horizontal tail there, and occasionally you'll see the upper rudder move. The control surfaces wiggle faster than they really did in this movie because it was taken at 4 times real time. The flight path angle was about 40 degrees here on this particular flight. And if the front lighting weren't so strong, I think we could see the shadow of the X-15 contrail on the desert floor in the background. This is looking over the pilot's right shoulder at the instrument panel. You can see the center stick moving around with no hand on it because the pilot was flying from the right-hand side stick, which is connected to the center stick. This shows the X-15 going over the top, and I can't really get a feel for how well you can see this. Not very well, I take it. We're now coming up. You can see the horizon in the background there. We're coming up over the top. There's no air up here, and the horizontal tail's trying to lift the nose, trying to help the ballistic rockets, so it was fully deflected. In this scene, we've now re-entered, and you'll see the pilot start a left turn back toward the lake bed, and then pretty soon we'll see the speed brakes come out. There's this, the upper speed brake deflected there.
One of my first jobs in 1960 as the X-15 propulsion engineer was to get my head, with only safety glasses and air protection, within 2 feet of the chamber while it was running at 1,500 pounds of thrust. I was to check for external leaks on the liquid oxygen check valve while the engine was running on the test stand. No doubt that would be not allowed today. The X-15 set speed and altitude records in the 1960s, reaching the edge of outer space and returning with valuable data used in aircraft and spacecraft design. As of 2012, the X-15 holds the official world record for the fastest speed ever reached by a manned aircraft. The X-15s landed on aft skids and the nose wheel on the Rogers dry lake bed at Edwards Air Force Base. Normal landing speeds were in the vicinity of 150 to 200 knots. However, an emergency landing made by NASA pilot Jack McKay on November 9, 1962 on Mud Lake in Nevada in X-15 number 2 was due to the rocket engine failure at launch at between 40,000 and 45,000 feet from the B-52 mothership. The landing was made at 257 knots without flaps as they failed to operate. Then one aft skid landing gear failure followed by the nose gear failure on touchdown caused the aircraft to dig a trough in the lake bed, traveling broadside and then flipping over. Luckily, Jack jettisoned the canopy as it was rolling over. The helicopter hovered over the wreckage, blowing the ammonia fumes away to enable the rescue crew to extract Jack from the cockpit. Luckily, no fire resulted from the crash. Jack's spine was compressed 1 inch from the hard landing, but he still flew 22 flights after the accident. Eventually, though, was severely disabled later. The helicopter crew and rescue crew were honored in the White House afterwards. After the accident, the X-15 No. 2 was rebuilt with drop tanks to extend rocket burn time from 73 seconds to 140 seconds. This photo was taken before the ablative coating was applied. Pink coating, then covered by a white coating, was applied to prevent pink flakes entering the propellant system through external vents, which would cause an explosion. The fuselage was lengthened by 29 inches to accommodate the drop tanks. The XLR-99 rocket chamber, which had 60,000 pounds of thrust, had an 8.5-inch diameter throat, and was made of stainless steel tubing carrying the minus 49-degree liquid ammonia fuel as a coolant. The tubing was coated with a ceramic zirconium oxide, trade name Rockide, applied at the Reaction Motors factory in New Jersey. This was by a rod-fed machine before the injector face was welded to the chamber. As seen at the throat, where the highest velocity occurs, serious erosion of the rockide is evident. The factory replacement of the chamber coating was taking a year, as the injector had to be removed for the rockide reapplication. We were running out of the 8 flight engines to support the 3 X-15 airplanes. I was tasked to solve the problem, and based on industry surveys, adapted a plasma arc gun, small enough to get through the throat. We developed a pantograph machine and mechanized engine rollover stand to deposit gradated coatings of metal and ceramics at 20,000 degrees to the stainless steel tubing without disassembly of the engine. Pure metal was applied to the tubing, gradating to a pure ceramic at the flame front. This proved to become a 1-week field repair turnaround. It even improved the life of the coating and ensured rocket engine availability. We turned the new coating machine over to the Air Force Power Plant branch, who then maintained the rocket engines. Prior art in 1928 for coating incandescent light bulbs squashed our patent application. The LLRV's first flight was made October 30th, 1964, 6 months after delivery to the NASA Flight Research Center, now the Dryden Flight Research Center, or DFRC, at Edwards Air Force Base in California. The electrical, rocket, and jet fuel systems were not installed, and all systems required completion of assembly and installation, checkout, and system integration testing. As project engineer for NASA, I had spent 14 months as the NASA plant representative during the design fabrication at the Bell Aerosystems plant in Niagara Falls, New York. Bell sent about 20 engineers and technicians to Edwards to assist us for over 6 months in the high-pressure Apollo schedule environment.
For takeoff, -1 on the H-dot. Hands off for your balance. 15 feet per second. Thank you. Deactivating. I'm hovering at 99%. Local vertical. Local vertical. Altitudes approaching 100. Left side, maybe we got 30%. Okay. There's about a 9-degree cross. Okay. Climbing. Balance is good. Thank you. And the wind is reading 25. Clear for landing simulation. Okay. This altitude is 300. There's 2 minutes to DB4, 50%. Thank you. Approaching 40% roll. Okay. Crosswind. Okay, lunar sim switch is on. Camera's on. Okay. Approaching. Speed should drop off now then. We're accelerating. Okay, now I'm showing a crosswind here of some magnitude. It should be coming forward now. Okay. Showing 32%. Okay, everything looks good. Auto throttle looks good. Okay, gimbal lock is off. Airspeed is yellow way up. Okay, on back in. Airspeed drops below 30. Descent rate's 10. Altitude's 200. it to 50%. Q. Descent rate 4. Altitude 100, descent rates 4, airspeeds 5. Touchdown.
This data plot of the Apollo 11 lunar module pitch attitude shows the dotted line of the planned landing maneuver, which would have been the black box for automated landing program. The solid line shows the actual maneuvers Neil was required to make based on the need to avoid boulders and craters as the LEM approached the surface. Realize these maneuvers were made with very low fuel reserves, close to the surface, also requiring very large pitch angles compared to those required by flying helicopters on the Earth at 1G instead of 16G. Neil's training in the LLRV and LLTV and his piloting abilities made him very comfortable with the landing, contrasted to his LEM pilot, Buzz Aldrin, who had no LLRV or LLTV training. The weight and balance fixture was used to determine the engine and the vehicle center of gravity, or CG. 3 scales, a clinometer, and a complex set of procedures were used to the following accuracy requirements driven by stability and control parameters for the flight research program. This included defining the lowest values of control authority for lunar landings to assist Grumman in the lunar module or LEM design. The exploration of the lower limits of control presented a real challenge to use the lowest control authority for the LEM landing stage, which was much heavier than the ascent stage that used the same attitude control rocket system. An over-controlled ascent would have resulted if the landing system control authority was too great. These research flights helped drive the LEM flight control system design to unexpectedly lower values of control authority. This meant real schedule challenges for the LLRV. This control authority testing required flight conditions with little or no wind. 1. The instrumentation had to be capable of determining the vehicle and engine center of gravity within 1/10 of an inch. The takeoff CG had to be controlled to 1/4 an inch sphere with some relief of the vertical tolerance that was made. And 3, in the in-flight fuel management CG had to be controlled to a 1/2 inch sphere. This evolved to require a roll trim control in the rocket fuel or hydrogen peroxide system for dynamic balance during flight. The LLRV weight and balance fixture was adapted to also serve as an attitude rocket system, hot firing closed loop checkout for the pitch and roll axes. Bungees were provided as soft stops. There were still adequate range of motion for initial system checkout and pilot familiarization prior to their first flights. This was used throughout the entire LLRV and LLTV programs for pilot familiarization, contrasted to the single-axis test fixture on the next slide, which was only used once prior to the LLRV's first flight. VTOL tether testing had historically a bad history as we were preparing for the first LLRV flight. This was the first fly-by-wire flight control system with redundant analog circuits with no mechanical or hydraulic backup systems. The previous slides showed the CG fixture providing adequate hot firing, closed-loop checkout of the pitch and roll attitude control systems. This left the requirement to have closed-loop or hot checkout of the jet engine running and its gimbal hydraulic system used for lunar simulation mode, with the rocket attitude control system operating for both the pitch and roll axes. The yaw axis was partially tested initially on the ramp with landing gear casters, which were later replaced with foot pads to provide more stable takeoffs. This LLRV single-axis test fixture was designed to provide the hot-firing closed-loop operation of the roll axis as shown here. Then by picking up the vehicle with the crane and rotating it, we checked out the pitch with identical system checkout procedures. This provided all the systems closed-loop testing required for the first flight without the risk of traditional VTOL tether tests. Custom bearings were made for the gimbals here. The reaction control system for the LLRV required both redundancy and a system design accommodating specific rocket engine locations on the vehicle. Corresponding Symmetrical placement of the propellant feed system tankage and components are required to achieve dynamic balance for fuel management during flight operations. The 6 emergency lift rockets are not shown on this schematic. This picture, taken from the 16mm film camera frame, shows the LLTV number 2 ejection on the 31st of January 1971 by NASA pilot Stuart M. Present. The loss of control was due to the recently upgraded main DC generator made by GE failing because of a hidden failure mode. This caused an unexpectedly high magnetic field being retained during the failure and preventing the switchover to the battery-powered emergency DC bus. As shown in this picture, the ejection seat rocket flamed out the jet engine and the DC generator RPM wound down, releasing the magnetic field so the battery-powered emergency DC bus came online. The analog fly-by-wire attitude control system came alive and the LLTV crashed due to lack of engine thrust, but landed straight and level due to the now functioning attitude control system. This hidden failure mode was the only one experienced in the 8 years of flying that the LLRVs and LLTVs experienced, for a total of 591 flights. This was significant credit to the design and development of the pioneering fly-by-wire analog VTOL aircraft that could provide earthbound free flight simulation for lunar landings. The loss of the LLRV number 1 and the LLTV number 1 were due to human error by the flight controllers on the ground, which resulted in the vehicle's loss of attitude control. Stu Present was killed in 1972 in a NASA T-38 accident. The seatman separator, or pyrotechnic rotary actuator, shown here is the one actuated in Armstrong's ejection, which was caused by lift rocket fuel exhaustion and inadvertent venting of the helium pressure gas used to feed the reserve attitude control fuel below the tank standpipe. This rotary actuator has been x-rayed in 2013, indicating no propellant remains in the actuator cartridge chamber. Notice the harness the pilot set on is wound up into the retracted position from the ejection sequence. The Weber ejection seat was a lightened version of the T-37 jet trainer seat. The LLRV spec required the entire seat assembly with its solid rocket motor, pilot's parachute, and rails had to be less than 100 pounds, a tough requirement. The seat system was designed with a precise CG controlled offset from the solid rocket thrust line by a little over 2 inches, just enough to ensure that the 500 millisecond burn time would result in the seatman assembly sweeping a 45-degree angle during the powered portion of the trajectory. This design statistically assured maximum reliability for the largest range of the vehicle attitudes at ejection. The CG offset resulted in an expected profile of the seatman assembly, performing a 2 1/2 forward tumble prior to the pyrotechnic butt snapper kicking the pilot out of the seat. The variation in the pilot's CG over time required that all pilots and astronauts flying the LLRVs and LLTVs be measured in a special CG fixture every few months in Weber's plant in Burbank, California, and their personalized seat cushions modified as needed. This ingenious system worked flawlessly 3 times out of 3 times, with no injuries, quite an accomplishment. To maintain LLRV, LLTV CG control, we used lead shot loaded in cans bolted on the legs to account for different pilot weights. The picture on the right is a live shot of a Weber volunteer riding the seat in a 0-0 condition from the lakeshore north of LA, quite a demonstration for future customers. The GE CF700-2V aft-fan engine was an aft-fan derivative of the GE CJ610 or J85, which completed its 150-hour qualification test in May 1961. The lubrication system was modified for the LLRV program to operate vertically, and soon after its commercial introduction on the French Dassault Falcon 20, it was put through a 50-hour PFRT, or preliminary flight rating test, in mid-1963 for the LLRV program at the GE Lynn, Massachusetts plant. I was the NASA plant rep at Bell then and participated in the test planning and execution. Its thrust was 4,200 pounds and weighed with accessories in the 800-pound range. Hot weather performance in the desert required operational compromises, as well as an exhaust gas pit to alleviate inlet recirculation due to the low ground clearance in operations during hot weather. The aluminum structure shown is a typical LLRV leg assembly designed with hydraulic struts with a landing gear to carry landing loads and represented decades of Bell Aerosystems structural design expertise. Their LLRV design provided ample safety margins, as minor flaws identified by conventional X-ray quality control inspections were controversial. Bell had 3 LLTVs on their shipping dock, ready for delivery to NASA in Houston in August and September of 1967. The then recent Apollo disaster, in which the 3 astronauts were fatally trapped in the capsule fire during a checkout, resulted in NASA's quality control exercising veto power via differences in weld inspection specifications over the Bell engineering traditions. A 2-month delay was experienced in the already late training operations. The problem was only solved by subjecting identically processed joints as shown to fatigue test many times the design requirements, which passed with flying colors. As the Bell LLTV technical director, this was my most formidable management and legal challenge to deliver LLTVs for Deke Slayton and the astronauts. This steel rig was used before the first LLRV flight to test the stabilizing drogue chute that was part of the emergency lift rocket system for the original LLRV design. The weight in CG was simulated for the LLRV, and the rig was flown to altitude by a Marine helicopter at El Centro Air Station and dropped, testing the drogue chute design and operation. On the LLRV, the 6 500-pound thrust emergency lift rockets were installed as a backup to the jet engine, which provided takeoff thrust and climb to altitude, and then 5-6G operation in the lunar sim mode on the 2 normal lift rockets. The jet engine never hiccuped once in the 591 LLRV and LLTV flights. The emergency lift rockets were never used and removed from LLRV number 1 after the last of 148 research flights. All future ops were for astronaut training. They were never installed on the LLRV number 2 or the 3 LLTVs. This was a wise move pushed through by myself and U.S. Army LLRV test pilot Colonel Jack Kluver. There was a high risk of failure on exactly when to utilize them to kill off the sink rate should the jet engine fail, as you never could be sure enough rocket fuel was on board. Houston ops were much better off to have the pilot or astronaut eject as soon as possible if the jet engine failed. This transporter was bid by a company in Oregon that built specialty trailers and was designed and delivered in 1964 for $800, a bargain not typical for NASA even in those days. As part of my early work, starting in 1969, to introduce air cushion vehicles in Alaska for the oil industry, I designed a new off-road tire and plenum control system for a wheeled air cushion vehicle. In 1975 to 1977, I performed consulting engineering and produced film progress reports for the Navy's 100-ton, 100-knot surface effects ship. Worked on the proposal for the 3,000-ton, 100-knot surface effects ship for Admiral Zumwalt's proposed 100-knot Navy. In the 1980s, I managed a video lab at the Air Research Facility in Torrance, California, to support gas centrifuge developments for uranium enrichment. This involved using the latest of imaging tools, fiberscopes, borescopes, video endoscopes, and high-speed imaging diagnostics. This high-speed system incorporated the newly developed copper vapor laser as a strobe light. It could be synchronized with a 2,000 frame per second camera tape recorder. The images were electronically split into up to 6 horizontal segments, resulting in 12,000 images per second per camera. Furthermore, to obtain perspective, 2 cameras were used, yielding 24,000 images per second by dividing the screen vertically as well. The tape recorders were limited to 45 seconds of recording time based on the 400-foot cassettes. This was long before the current capacity of solid-state memory was available. And we needed perhaps 10 minutes of recording time due to the test procedures. I had the vendor design a signal processor to accept inputs from both cameras and feed the images to 2 different tape recorders simultaneously. This required the technician to remove one cassette near the end of the tape from the first recorder just after starting the second recorder. It worked. This first failure of a test part was captured with 2 master images as it failed during the recorder switchover. This project saved the DOE from transferring about 50 engineering positions over to another contractor, as we were able to know exactly where the new parts were failing and provide a design fix. Getting the laser beam in and out and the images in and out of the spin tank of thick steel was not easy, but done with beam splitters, mirrors, and Lexan ports. Assuming an object was traveling at orbital speeds of 18,000 miles an hour, the system could provide a blur-free image with the distance traveled during the strobe exposure of only 12 mils and give those images for every 54 inches of travel. In 2008, as part of the now canceled NASA Constellation program to return to the moon, for the new lunar lander Altair project, I participated as a NASA SAGES consultant in a trade study to look at current technologies best suited for Altair lunar landing training. This title page from the resulting study depicts the potential training resources available that were included in the study. The next 2 slides amplifies the findings. The trade study examined the pros and cons for the best 3 candidates: the gimbal jet, the air crane, and the VSS Variable Stability Seahawk helicopter. The AV-8B Harrier VTOL and the V-22 Osprey tilt rotor were eliminated from the viable candidates as unsuitable for the mission. The green bars represented superior suitability for the mission. The yellow degraded but acceptable suitability, and the red unacceptable. The gimbal jet approach used in Apollo ranked the best of the 3 choices, in part due to the next commentary by Apollo 17 Commander Gene Cernan. Training effectiveness metric. There is an aspect of training that goes beyond fidelity. One can have all the cues right, all of the visuals right, etc., but still miss something critical to the effectiveness of the training. Gene Cernan summarizes succinctly: you have to eject or land. Those are the only 2 options. Think of it with this analogy. The ultimate training to learn how to fly an aircraft is to go fly the aircraft. For a moon lander or other destination beyond low Earth orbit, there is no such analog. You work with the next closest thing you can in an Earth analog, an Earth lander. But just as in the airplane, you have to make the landing. Something beyond the fundamentals of the physics needs to be put into the psychology of the task. I must make this landing. I can't rely on anyone else. If I don't make this landing, really bad things are going to happen. So in this case, the fidelity of the physics is not nearly as important as the fidelity of the psychology. So physical effectiveness is important, but psychological effectiveness is also very important and must be taken into account. That is why this metric is here. There is something in the concept, training with real consequences, that is meant to be captured here.
Apollo 11's running short on fuel is widely known. It's been widely discussed by the press and others, and even in mission control here, people were biting their nails as to whether I've been flying the machines at Elton. We took off with 9 minutes of jet fuel and someplace between 90 and 100 seconds of altitude. So we were always landing with 20 or 15 or 20 or 25 or 30 seconds. We had to. And so it wasn't very much of a concern to me in Apollo 11 because it was just like what I was used to. And if I made a mistake, it would be a bad one. So I think that was, Dave Scott thinks this is one of the more important aspects and one that I haven't really thought much about. But he does think that that's an important skill, let's say, important experience to make yourself have the mindset to be comfortable in a short fuel situation. So
Neil says it exactly the way I feel. You know, to me, it's at one step closer to the real world. You're out there at 400 or 500 feet. You got 5 minutes of fuel, 15, whatever the hell it is. It's only you and your maker. Okay? You're running a problem in the lunar land, in the LMS, in a simulator. You have a problem, you go topsy-turvy, you land into a crate, push the freeze button. Let's go out and have a cup of coffee and talk about it. When you're in the environment Neil's talking about, you don't have a change, you don't have a freeze button. You're going to either do it or not do it. And I want to know that I can do it and feel comfortable before I get out there 250,000 miles away and have to do it one time successfully. I think putting yourself in that environment, quote, a risk environment. You know, John Dryden, I don't want to crash an LLTV, but I'd rather have the option of screwing up here and learning something and getting out of it and doing it again, because I don't have that option when I'm landing on the moon. And so there's a lot of psychological effects to the comfort level I think we gained when we were in that real world, in a lunar module, landing on the surface of the moon, that we gained because of the environment we found ourselves in the LLTV.
I mentioned also with the aspect regard to your earlier question, you do often change your landing point at some point after you're on your final approach. And a lot of the guys flying the practice sessions would intentionally change their landing point from the place where it was going and make themselves do that. It is, I grant you, I believe that aspect can be covered by many of these competing aspects, but it is an important part of training.
Also the 6th degree of freedom concept simulation you found yourself in. I don't find myself in a helicopter in a 6th degree of freedom mentality. I just didn't. I'm flying over there. But this one, you could drift over there. And if you intentionally put the drift in that we all did when we got familiar with what we were doing, you had to take it out. And we would pick a spot out there at Ellington to land on, and you'd force yourself to go in another direction so that you'd have to force yourself to correct. It was the environment that you found yourself in, and that you were there alone. You look over your shoulder, there was nobody there. You were going to land it, or you're going to pull the ejection seat. You're going to do one or the other. And I'd rather have that option here, because I didn't have it on the surface.